Welcome everyone, and we're going to continue our discussion on exercise metabolism. In this particular video, we're going to discuss the metabolism effects from the recovery during exercise and in particular metabolic responses to exercise and how it respects to intensity and duration. So before we get into that, let's do a little bit of review. In our previous video, we defined metabolism and what it was. And to recap on that, metabolism is the sum of all the cellular reactions in the human body. This includes all anabolic and catabolic reactions. Now, metabolism at rest is different than metabolism at exercise. We introduced the idea of basal metabolic rate, or BMR, and this is the sum of your metabolism at rest when you're not doing anything, and how it changes going from rest to exercise. And so in the initial minutes of steady state exercise, we say that ATP demand outweighs ATP supply. And we showed this through O2 debt. And we had said that it takes the body upwards to about 1 to 4 minutes for ATP supply to meet ATP demand. So what happens to our metabolism during the recovery portion after exercise? Well, let's answer that question. So oxygen uptake remains elevated above rest during exercise recovery. And the one way we can look at this is just by looking at heart rate after an exercise. And so what we have here in front of you is an athlete's heart rate data after they performed 30-second sprints with 30 seconds recovery on a bike. And so what had happened here is after the main set, the athlete performed just under 10 minutes of cool down. And so if we look right here roughly at the 19-minute mark is when they stop cycling. Heart rate stays elevated for a fairly long time and doesn't drop off and reach close to resting levels until almost 1 to 2 minutes after exercise. And this is what we're talking about, is we can infer that you have the increased O2 uptake because we have the increased heart rate as well. Now, if we had had a respiratory monitor on the athlete, we'd be able to see the increased respirations during the recovery portion of this exercise. And so why do we have this increased oxygen uptake after exercise? Well, the idea is that the body's repaying the O2 deficit at the onset of exercise. Again, going back to our graph that shows the oxygen deficit when we go from rest to steady state exercise, we have the oxygen deficit because it takes ATP supply to meet ATP demand. And again, we said this can take anywhere between 1 to 4 minutes. And so we call this repayment of the O2 deficit that we see at the onset of exercise as excess post-exercise oxygen consumption, or EPOC for short. And so what we have here in front of you is an expanded version of our rest to exercise graph. So again, here on the left-hand side, we have rest. And then all of a sudden, you go into the treadmill and you start exercising. You increase the speed to 7 miles per hour. And then you hold that same speed for 6 minutes. And then to this point, this is where we stopped on our previous graphs. So continue with that example. Let's just say you dropped the speed and went straight to 0 and went to sit back down and not moving. And so what we see here again on the left-hand side is our O2 deficit that I'm highlighting here in purple. Because again, it takes ATP supply to meet ATP demand. And roughly here at about the 3 to 4 minute mark, ATP supply is meeting ATP demand. This concept is what we discussed in the previous video and quickly touched on during our review at the beginning portion of this lecture. Now, looking at the recovery side of things, which is again right here, because this here at minute 6 is where we made our speed go from 7 miles per hour to 0 miles per hour and decided to just sit down. And so what we're seeing is that the respiratory rate is still pretty high, and it takes time for it to drop off. And so with the increased heart rate and increased respirations, we still have an increased oxygen uptake, and it takes time for it to reach back down to resting levels. And so when we look at EPOC a little bit closer, it can be divided into two subcomponents. The first being the rapid component, and the second being the slow component. And the way you determine the difference between rapid to slow is the rate of the oxygen uptake. If we look here at our graph, the oxygen uptake slope up to right here is very steep. And at this point, we have an inflection to where the rate becomes less and less. And this inflection point right here is the determining point between the rapid component and the slow component. And so if we focus right now on the rapid component, you can tell that the rapid component of EPOC ends pretty quickly, usually within 1 to 3 minutes after exercise is completed. And research has shown that the rapid component of EPOC does two things. One, it replenishes stored phosphocreatine. And secondly, it replenishes muscle and blood oxygen stores. This replenishment is highly necessary because the body needs to continue to work after exercise. Let's think about how you exercise on a normal daily basis. A lot of us continue to do a workout during lunchtime. And so you go through and you do a steady state run and you complete the exercise. We don't have the luxury of falling asleep immediately after the exercise is completed. We need to continue to go on with our daily lives. And so by doing this, by replenishing the phosphocreatine stores and the O2 stores in the blood and muscle, the body is able to continue on with its basal metabolic processes and work to be able to continue throughout the day. Now, looking a little more closely at the slow component of EPOC, this particular component can last from anywhere from a few minutes to several hours. And this is all dependent on how intense the exercise was. And the slow portion of EPOC, you will still continue to see increased heart rate and breathing. Usually, a lot of this is due to the increased catecholamines, known as norepinephrine and epinephrine, still circulating in the body. Also, during this portion, we'll still continue to see increased body temp. And this is mainly due to the continued increase in the metabolic rate post-exercise. And finally, probably the most important portion of the slow component of EPOC is the conversion of lactate to glucose. And this occurs via the Cori cycle. And so the reason why the conversion of lactate to glucose is important is because this shows that lactate is also a form of energy. And so the body is able to utilize a byproduct of the glycolytic process, particularly from the anaerobic glycolytic process, to be able to replenish its own fuel source. Now, another aspect of EPOC to keep in mind is it is highly dependent on the intensity and duration of the exercise. And so going back to our steady state example, our O2 deficit was not too high. But let's say we have someone performing a high intensity exercise. And so what we find is during high intensity exercise, the intensity of the exercise rises really quickly. And so that means that with the increased intensity, we have a greater demand for ATP. And so again, with the initial portions of exercise, it takes the ATP supply pathways time to catch up. And so what that means is the initial O2 debt is much greater than what we see here under steady state conditions. And so with this greater O2 deficit in the beginning of exercise, the epoch is much longer as compared to the steady state. And so what we find is the rapid component of the epoch doesn't change too much as compared to the steady state. It is a little bit longer, but not too much. But the greater difference we see is in the slow component. We see that the slow component of the epoch lasts much longer. And why is that? Because this goes back to our energy pathways and with the respect to intensity versus duration. And so if we have an exercise that is a very high intensity, this means it's got a very low duration. And those types of pathways that we discussed that fit this profile are typically going to be the PCR pathway and the anaerobic glycolytic pathway. And especially with the anaerobic glycolytic pathway, the one byproduct that we see with this is lactate and hydrogen ions. Because again, the pyruvate that is created at the end of the anaerobic glycolytic pathway is converted into lactate and the hydrogen ion due to the enzyme of lactate dehydrogenase. And so what we'll see is at the end of high intensity exercise, you'll have large concentrations of lactate and hydrogen ions being produced. And so it takes the body much longer to recycle these two byproducts of the glycolytic pathway. And so again, we had stated that the most important concept of the slow component of epoch is lactate clearance. And so it's not too far to understand that if you have greater concentrations of lactate, it's going to take much longer for the body to clear it out. We covered a lot under this concept of epoch. And so let's summarize the factors that contribute to increases in epoch. The first is the amount of phosphocreatine that needs to be resynthesized in skeletal muscle. The second is the lactate conversion to glucose. And again, this is what we stated as the most important component of the slow component of epoch. The third factor is the restoration of oxygen stores in the blood and skeletal muscle after the exercise is completed. Next is the elevated body temperature that occurs while the body is still trying to recover from the exercise. Next is the elevated heart rate and respiratory rate after exercise. And finally, the elevated hormones. Because again, some of the elevated hormones that we mentioned were catecholamines, which is norepinephrine and epinephrine. And these are known to cause increases in heart rate and breathing. And so if you look at these factors, we can identify which ones affect which components of EPOC. So, for example, the resynthesis of phosphocreatine in skeletal muscle and the restoration of oxygen in the blood and skeletal muscle, these deal with the fast component of EPOC. Now, if we look at lactate conversion to glucose, again, we said that was the most important factor. Elevated body temp, elevated heart rate and breathing, and elevated hormones. These all deal with the slow component of EPOC. Hopefully this helps keep EPOC straight and the different components and factors that affect it. So during our brief discussion on the slow component of EPOC, we stated that the removal of lactate is one of the most important factors of the slow component. And so why is this important? First off, lactate can be converted into glucose via the Cori cycle. And this occurs in the liver. But recent evidence shows that only about 20% of the total lactate that is produced during exercise is converted into glucose via the Cori cycle. What current evidence is showing us is roughly about 70% of all lactate is oxidized by cells. And the remaining amount, which is roughly about 10%, is broken down into amino acids. The reason this is brought up because under classical theory up until a few years ago, it was thought that the majority of lactate was converted into glucose. And current evidence is showing that this is not the case. Another important concept that recent research is showing us is that lactate can be cleared through passive means. And so what we mean by passive recovery is sitting around or doing nothing right immediately after the exercise during the recovery period. Now, what recent research is showing is if you perform light exercise, optimally between 30 to 40% of VO2 max during the recovery period, it significantly increases the rate of lactate clearance. So what we're saying is during the recovery period, if you perform light exercise, the body clears out the lactate faster and it promotes quicker recovery. And so within this concept of EPOC, we discussed, O2 deficit and the excess post-exercise oxygen consumption. There's two key factors that can come out of this, or key concepts. The first is a warm-up. Even though we directly didn't speak about it, is if you do perform a warm-up, you reduce the O2 deficit at the beginning of exercise. By preparing the body for exercise, it allows more time for the ATP production pathways to equal out the ATP demand at the beginning of exercise. And the second component is what we directly stated, is if you perform active recovery during the recovery portion of exercise, you increase the lactate clearance after the exercise is completed. And by doing this, you help promote faster recovery and are better prepared for the next workout session. And this could all, by understanding these two concepts within all this can help enhance performance of the athlete or subject that you are working with. This video is slightly longer than the typical videos that we put out, just because the two subjects for this lecture go together very well. And so what I suggest is pause the video here and take a quick break and come back. And so when we start looking at exercise duration, we have to start talking about environmental factors that start affecting metabolic responses to the exercise. And so we are in agreement, first off, when exercise is greater than 10 minutes, at this point, your entire ATP production is through the aerobic pathway or oxidative phosphorylation. And when this exercise is at a steady state, at an intensity of what we call submaximal, then the oxygen uptake can be maintained. Now, when we start introducing environmental factors such as heat and humidity, some of these factors that we've discussed, such as oxygen uptake and so forth, things begin to change. And so when we look at prolonged exercise or high-intensity exercise in a hot or humid environment, what we see is a right shift of the VO2 or oxygen uptake curve. And so what do we mean by that? So let's explain this in graphical format. And what we have here is on our y-axis, we've got our VO2, which is in liters per minute, or our oxygen uptake in liters per minute. And here on the x-axis, we have time. And so what we're saying is we're going to start our graph at 10 minutes because we want to show that we're completely aerobic at this point. And so let's say we have our subject is continuing to run at 7.0 miles per hour. And so with our first example, we're going to say that he's running on a treadmill at 7 miles per hour. And so what we see is we have this general increase, but then a steady state of the oxygen uptake under normal conditions, say with them running the treadmill indoors. And so typically when we look at the environment indoors, the temperature is steady, typically at 72 degrees, with humidity usually at about 68%. Now let's say the same athlete wants to run outside in a hot, humid environment, say in Miami, Florida, at 7 miles per hour. Well, what we'll see is an increase in that oxygen uptake. Additionally, it's not maintained at a steady state as what we saw on the treadmill. It can continue to increase over time due to the humid environment. And so right now, at the time of this lecture, the temperature in Miami is 98 degrees with a humidity index of 90%. And so why does this occur? In this hotter environment, we have increased body temperature. Because the body has a more difficult time in regulating the temperature in the hot and humid environment. Additionally, we have increased concentrations of catecholamines of norepinephrine and epinephrine. Essentially, what we're saying is the work is harder in a hot and humid environment compared to those under normal conditions. And thus, what you can see with this is the steady state of the oxygen consumption is not achieved in the hot and humid environment. Another aspect I want to discuss briefly is the metabolic responses to incremental exercise. And when we talk about incremental exercise, we're talking about exercise where the intensity increases over time in almost a stepwise manner. A great example of incremental exercise is through VO2 max testing. And what we have here in front of you in this diagram is a picture of the results of a cycling VO2 max test. And so right here, this was the starting point of the incremental test where the subject was riding at 100 watts. When at the end of the test, he ended at 480 watts. And so over this 18-minute test, the intensity increased throughout the time. And we see that here with this yellow line. Additionally, you can see how the heart rate, which is the red line, increased over time as well. And so what we see with this is the oxygen uptake increases linearly with intensity. And again, under regular everyday circumstances, we can kind of see that with the increase of the heart rate throughout the incremental test. And so the aspect that we see with the oxygen uptake is it continues to increase linearly, but it does have a ceiling. And the ceiling is called the VO2 max. And at this point, the VO2 cannot increase anymore. And so what the VO2 max is, it's the physiological ceiling for the delivery of oxygen in the muscle. And it is governed particularly by two components, genetics and training. We'll get more into this concept later on in this course. Another key concept that you'll see with prolonged exercise is this concept called lactate threshold. And by definition, lactate threshold is the point in which blood lactate concentrations rise systematically during exercise. And so if you're taking blood lactate concentrations, these are concentrations greater than 4.0 millimoles per liter. It's also called, sometimes in other trade books, as anaerobic threshold. And the reason it's called this is because any intensities greater than lactate threshold fall within the anaerobic pathways. There's more to this concept of lactate threshold and training at lactate threshold, but we'll get more involved with this concept later on this course when we dive into more detail about the VO2 max. So in this video, we covered a couple of different areas. The first is we discussed what EPOC, or excess post-exercise oxygen consumption, is, and also its two subcomponents of fast and the slow components, and the factors that govern those and what they accomplish. Secondly, we discussed the effects of prolonged exercise on metabolic rates. Thirdly, we discussed the effects of incremental exercise on metabolics. And then finally, we introduced the concepts of VO2 max and lactate thresholds. I hope you've enjoyed this video. Take care, and I'll see you in the subsequent videos.